Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about CATL, C-A-T-L hybrid battery. Basically, I'm focusing on a hybrid battery. This company has made some recent announcement, so let's dive deep into it. So what exactly is the problem? Well, problem is there is something known as periodic table, and that created a problem. That created a problem that we do not have magical cell chemistry. We want one cell to do everything. We want one cell to have power, one cell to have capacity, one cell to be cheap, one cell to be safe. Yeah, chemistry is like, nah, bruh, nah. Chemistry is like, have this. And be mindful, this is just surface level. There are people whose sole job, PhD level, multiple PhD level, whose sole job is just to dive deep into one of these chemistry. So there are experts who are just expert in lithium iron phosphate. And like, isn't that complete? No, there's special spices that goes inside that. Then you have nickel, manganese, cobalt. Then you have nickel, cobalt, aluminum. Then you have cobalt oxide. Then you have manganese oxide, and my personal favorite, lithium titanate oxide. So, but here's the deal. Outcome is all of them have different strength and different weaknesses. Meaning, this puppy has the highest specific energy, JJ. Safety, performance, lifespan, While compare that to LTO, those puppy have performance, lifespan, JJ, safety, ultra GG, satellite safe, and specific power, reasonably good. Specific energy, lol, what is that? So that's the reality of it. Every chemistry that you look into it, and let the picker, this is just a rough idea. Same was true, same is true, same will be true. So fundamentally, it just becomes a game of compromise and balance. So inherently, things that give you a lot of power generally are very short-lived. For example, lithium titanate oxide, these puppies are the most powerful one. Like 10 amp shock is like, bruh, don't wake me up. 10 C shock, bruh, don't bother with me. Like these puppies can directly do spot welding. That's how strong they are, and without degradation. They can charge from 0 to 100% at 4 to 5 C and still have lifespan of 3000. Then why don't we use it? Yeah, it does not have capacity. Meaning your giant bike would barely have 10 to 20 kilowatt hour. So it has everything. We do use it in very serious application. It's just that it does not have the capacity. While other things that have like bonkers amount of capacity, like range wise, bonkers. Everything else is like, yeah, God help you. Like cobalt, aluminum oxide, safety. What is safety? One minor puncture, kaboom, sir. So that's a very serious issue. So some give you great of almost everything, like, it averages out in you like, hey, you know what, this could work, and then they are unaffordable. They require some material that is too goddamn expensive. So fundamentally, and again, physics, engineering, economics, if you cannot satisfy the economic layer, it does not matter. So we have to find something that can manage it. And environmental conditions are also a big deal. Now, again, if you are making an electric vehicle in India, likelihood of you are seriously worrying about hot climate is much higher versus cold climate. Like even like in Himalayan places, like cold is not really that cold. Like I was never familiar with the fact that you could have a scenario where a mobile can freeze inside a vehicle until I looked into how people have to design vehicles for Alaska. I was like, oh, things can go cold. And then there was Russia. I was like, yeah, bro, we go cold. So again, completely different. You cannot use the same chemistry. So all of these go into it. So we have to figure out a way where we can solve all this problem without going into magical solution. So right now, chemistry is the main fact that we have to deal with it, and we have to find clever engineering around it. Chemistry is sorted. We just have to find an engineering way around it. So what is the logic behind it? Well, logic is, what if you have two chemistry working in sync? That will solve all the problem. For example, concrete, GG stuff, super cheap, strong. In compression, that puppy is like, I do not give a damn. Like this puppy is like GG. But here's the in tension, it will crack like there is no tomorrow. It's like kaput. So what if you had rebars into it? Rebars under compression, it will bend. It's useless. Under tension, it's like, I got this, fam. What if you have both of these together, married together? Now you have reinforced concrete. No problem. You build whatever you want to build, and that puppy can last for a century as long as it's well maintained. So what if we do the similar thing? Not just try to do everything with concrete, not just try to do everything with steel. What if we have both of them make love together? So that's the whole idea. You have one thing that gives you power buffer. And as in, if you apply an accelerator, you need bonkers amount of power to yeet your car. And again, same goes in reverse also. When you apply brake, you also need something that can eat power like there is no power, as in kilowatt. And then range, requires kilo energy tank, aka kilowatt hour, how many units of the capacity you have. So these two, generally chemistry that is good in this generally is bad in this. What is bad in this is generally good in this. So you have to balance it out. Heck, you can even see 18650 cells. It's very easy to figure out. Go into any seller that gives you a lot of options, find something that is rated for 10 amp output, and then find something that is rated for 40 amp output. And like, okay, wouldn't that be better to just buy 40 amp hour? Until you look at its capacity. It's like, bro, why the capacity is half? Yeah. So one gives you power, one gives you energy. You just have to make sure both of them make love together. And sometimes, especially for European customers, because they are familiar with this puppy, is that you need something that is temperature resistant. Now, here's the interesting part. If you directly started to charge a battery pack that is not rated for that temperature, it will hurt it. But what if you have something smaller, something adjacent to it, that you start to absorb power instantaneously, and that will slowly charge it up. First, it will heat everything up because it is getting electricity just from waste heat itself. It will start to heat everything up, so that's good. So everything is safe, everything is in sweet spot, and then you start to dump back power. So that's how you fix basically temperature resistance and capacity. So you have something that can work instead of minus 10 degrees Celsius cap, it goes to minus 40 degrees Celsius, meaning this puppy can handle Russia. So temperature resistance, I'm talking degrees Celsius. So temperature resistance, capacity, both of them can be specified. And you can mix low cost with high performance, as in there are many chemistry cells that are super cheap. You can just buy it, don't even think about it. But here's the, you will know that you are driving those cars. Why? Because you press the accelerator, even if motor is like, I got this. Even if motor driver is like, I got this. Battery is like, relax, bro. High internal resistance, bro. Chill, bro. Slow amount of amps, bro. So you're like, what the hell is happening? So what if you have something low cost car, but you have enough of a power package into it, where it's like person presses the accelerator, car just go. Everybody will like buying it. So, and again, low cost cars have to sell in higher volume. So how do you make sure people buy in higher volume? Experience the feel. So how do you experience the feel? Have higher power oomph. Small burst, but that alone will make people's experience like, whoa. So low cost chemistry with high performance. Again, you do not mix it one-to-one. You mix it like, 90% low cost chemistry, 10% high power, or 30% high performance, 70% low cost. That's how you balance it out. But let that be very clear. Doing all this does create an issue where BMS is no longer good enough. You have to go above BMS, what we classify as PMS. Power management system, meaning because generally you are talking about two chemistry, even inside lithium, not only going from lithium to sodium, generally you are talking about something that has different voltage curve. So that because of that different voltage curve, you do need a way of managing system. Failure to do so will cause bad things to happen. So you need something that can manage two different voltage level and voltage curve. And let's say you have something like a power buffer pack, it also has to be drained while you are driving the car. It's like, okay, why you have to drain it? Well, if it's not empty enough, it will not absorb the regen charge. So many car companies nowadays have a spare capacity that they never expose it into your dashboard. Like, and again, BMS does not allow it to charge to that level. It only allows energy to go into that sector, so to say, is when it's detecting it's coming from regen. So you can absorb. Many cars had that issue, as like if they exposed all of the range, cool, awesome, GG, but people will charge it to full. So when you're starting, it will always have to apply mechanical brakes rather than regen. So to have a consistent regen feeling, you have to drain your power buffer. Power buffer should be, let's just say, if it's well designed, 50%. It has to be at 50% level. So this is the logic behind it. Basically, you combined best of both worlds. It allows you to make it cheaper. It allows you to maximize profitability while reducing the penalties. So we go into what we call hybrid battery system. So lithium iron phosphate and lithium titanate oxide, these two make good love together. So one is great for capacity, like if you want kilowatt hour, as in like I want hundreds of kilometers of range, your lithium iron phosphate is like, I got you, fam. But you're like, okay, I want to press the accelerator, and I want to press brakes, and it's like, boom. For all that, titanate oxide is like, I got you, fam. And by the way, titanate will also allow you to do fast charging. Now, let this be very clear. Every company will try to trick you. It's like, we have 4C fast charging, meaning you can go technically go from 0 to 100% in 15 minutes. Can that be done? Easy peasy. Will that be done? No. Why? While lithium titanate oxide can easily digest it, that's how they are tested. Yeah, lithium iron phosphate will go kaput. And that's why I pay attention to all smartphones. All laptops, all of them will say 0 to 80% in like few minutes, and then it's like 1 hour. Lithium, no other than lithium titanate oxide, almost all chemistry requires 1C, meaning you can charge 0 to 80 as quickly as possible. 80 to 100% will take a lot of time. Why? Well, 0 to 80, it's what we call constant current. You are dumping current. You can dump current as much as you want, as long as you can keep them cool. But the moment current reaches a certain point, state of charge reaches a certain level, generally at 80% or 90, depending on how chemistry powders have been spiced up, you reach a point where you have to switch from constant current to constant voltage. Constant voltage is like trickle charging. So the idea is this can give you a lot of kilometers in very short while. Like you plug the plug in, go and like pay, come out, pull out the plug, you would have dumped 100 kilometer of range. How would that happen? Well, the range will go into lithium titanate oxide first, and titanate oxide will slowly start to slow charge your lithium iron phosphate. So that's how you're mixing both of them. And again, that will be your primary system, because again, it has to be drained so you can do regen reliably, and it has to be there so you can do acceleration reliably. And iron phosphate is like, it's fulfilling it. And that was one option. Then you have another option, that is sodium ion with lithium cells. Now, if you know anything about chemistry, you know for a fact that sodium is flat out nowhere comparable to lithium. Like the worst lithium chemistry, sodium still looks like, bro, you gotta have more power. Like sodium does not have power, as in like a kilowatt hour is just not there. That's why we do not use sodium batteries. But if done correctly, sodium has two core advantages. First, it handles low temperature like a champ. Like if you are minus 40 degrees Celsius, sodium is like, I got this, me good, I got this. Second, if built correctly, it also has very high surge current capabilities, meaning its C rating is very high. So it is almost like a power buffer. So instead of having lithium titanate oxide, you can have sodium, like this puppy. Sodium battery with lithium iron phosphate. That's a dual battery system. So benefited main energy zone can still work at minus 40 degrees C. And here's the funny thing, once you charge it, there is enough waste heat that that will slowly start to warm up all other cells, and you will reach equilibrium, and then you can safely charge them also. So you do not get the penalties like, hey, I dumped energy, but most of the energy was lost in heating. You do not have that penalty. So a lot of improvement happens just because of this system. So basically, it's almost like how you have rebars in concrete. Sodium gives you cold temperature resistance and fast charging. And EV can also perform better. That's the whole point. That's why everybody wants to do this, because instead of having an EV that's just like, oh, it's a cheap EV. Nobody should say that. Nobody will buy EV. And again, if you looked into fuel consumption of the planet, you know nobody buys EV. You're like, no, EV is selling. No, EV is not selling. How do I know? Look into every country. Go YOLO on it. Every country that has population, go YOLO on it. Like top 10 populated country, India, China, USA, Russia, Indonesia, Pakistan, go YOLO. Okay, all of them, top 10. Majority of the Earth's population. Outcome is none of them are buying EV. None. Zero. Zilch. Crude oil consumption is going constantly up, including petroleum. Including specifically petrol, as in gasoline. I'm not even touching diesel. Diesel is not going to, and you can't say population is growing. Population has been stagnant. It's going down from 1990s. Because nobody buys electric. Because if you can afford electric, you are filthy rich, and there is a very good chance you have electric and a combustion car. And you will buy electric, and then slowly it's like, yeah, we really are very good at ignoring what happened to the first batch of people who bought electric cars. Not good, let's just put it that way. And people who are poor, who really want to get into electric, they buy something and it is so horrendously bad, because again, the chemistry engineers were stuck. They were like, hey, if we give them lithium iron phosphate at this sort of small capacity, as in let's say 30 unit battery, we can't give them enough amp. The battery, like motor is there. Motor is like, motor, I got this. Just give me amps. Battery is like, I can't give you amp, I have too high electrical rhythm. But here's the deal. Imagine you shrink that. Instead of 30 unit battery, you have 20 unit from lithium iron phosphate and 10 unit from sodium. That's cheaper, and you have that. And that puppy is like, I got this. I can give you the amps you need. So then you press the accelerator, it feels alive. The car feels GG. Apply brake, it's like stops like a fast and furious vehicle. So that performance boost on lower cost is sure to uptake money. At least we should be able to reduce petrol consumption. Only time I have seen crude oil consumption go down is in pandemic. So fundamentally, and again, the most sustainable part of it, increasing lifespan of the battery pack, meaning instead of lasting, let's say 10 years, it can last 20 years. It's like, why is that? Well, sweet spot. Meaning, if you look into chemistry, cell manufacturers, whoever you cell, be it Panasonic, be it Seata, be it Tesla also, whatever cell manufacturer you look into it, they will always tell you, like, keep the battery from this to this range and always drain power in this range. It's good, but you can't guarantee that, especially if it's only what we call electric vehicle. If it's a hybrid, engine is a backup. It's like, okay, do not drain it below, let's say 20%. Computer will be like, hey, battery is reaching 10%. It will say, hey, can you charge it? It's like, no, I'm driving it, cool. Engine is like, I got you, fam. Engine turns on and starts charging. So your battery lasts much longer, you get much better lifespan. But again, people do not like that. So now you have two chemistry. Both chemistry are reinforcing each other. Exactly how rebar is reinforcing concrete, how concrete is reinforcing rebar. Now you can have a scenario like, don't drain too much power. It's like high power chemistry is like, I got this. Don't drain energy from high power chemistry. It's like, I got this. So you are reinforcing both of them. Lifespan is the best advantage for low cost customer. If they buy something, and again, this company is specifically focusing on hybrid. And again, people are realizing thou shall have hybrid, otherwise nobody will buy electric. Like electric has been going on from 2008. Zero penetration, like real impact wise. It's almost like, oh, we had a pandemic, we created a vaccine, the pandemic count went up. And people are like, electric. No. Stop looking at some tiny nation in Europe where it's like, oh, there's 15 people have bought it. No. Look into crude oil consumption. Constantly going up. So fundamentally, you have to create a battery bank, A, which people can afford, B, that lasts long enough to be comparable. Like you cannot expect poor people to buy, like I am a poor person, so I can't just buy an electric car and just yeet it in few years. And right now, the cheap electric cars that I would be able to afford after taking out a huge loan, yeah, most of them will be kaput in few years. That is not okay. So fundamentally, increasing lifespan, that is the most beneficial outcome for everybody involved. Except these companies like, yo, nobody is buying more new cars. But again, at least enough car will be sold. So finally, the car selling will be like, oh, it's actually matching a crappy failed car model. Like, please look into like how many electric cars are sold versus how many units of a flop car model is sold. You'll be shocked. Even in 2025, I'm working with car engines, so I'm dealing with it. Now we come to another aspect. What if you are not happy with battery only? Hybrid energy storage is the solution there. Meaning, let's say you are happy with the chemistry. Let's say you just want, hey, I want a cell chemistry that is good enough, and you are finding, let's just say lithium iron phosphate right now is the sweet child of everyone. So you're like, hey, it's available for reasonable price. It has more than enough capacity. It just does not have the lower internal resistance where I can just dump energy into it. So what if you mix that puppy with capacitors? Doesn't capacitor have a different voltage code? Yes, you have to design it, but it's a good mix. Why? Capacitors are great at tanking spikes. Meaning, if you have a supercar that is racing and you're applying brake only like kilowatts of energy or even almost touching megawatt of oomph going into your system, battery will go catch on fire if you do that. Capacitor, are you doing something? It's like, wake me up if it's interesting. So capacitors, like, it can tank it. This is a very good example. Like a battery is a big jug, but has a very small throat. It's a small bucket, but like wide throat. It's like, so utilizing capacitor, it can tank it. Meaning, if you apply regen brake, it's like, I will slow the car down. You will not even touch your mechanical brake. I will stop the car. That's how strong these things are. And when you are accelerating, it's like, oh, you sure? Do you want to accelerate? It will ask, it's like, bro, are you sure? Because I can go. And trust me when I say this, electric motors are brutal. They can accelerate. So as long as you have power. Now this puppy will outspike any lithium chemistry, like on a fundamental Faradic level. So that gives you the best spike performance, supercar performance level. And many electric EV already have it. Like, heck, if you look into manuals that are sent to fire brigade, where they're like, okay, how the heck you're supposed to handle with fire, they generally give a very good technical breakdown. What the heck is there? All Teslas have super capacitor. Small pack, but they do have it. Again, I do not know exact manufacturer and all that, but like there is a small, which again will help them out. Many others also do that. Some have big ones. Most of them have small one, but you always want something like, take the edge off. Like Toyota TS030, this puppy, and IndyCar hybrid series are also introducing that because again, they realize that's a very good place to use. You have battery that gives you enough oomph for long enough, and you have capacitors like, I handle this. Like, capacitor can handle it. And there are somebody who's figured out, hey, what if we put it in normal combustion car? Like even a low cost combustion car. It's like, is there a benefit? Actually, yes. For example, you have lead acid battery. You must have seen, especially if you have low cost car, like I have Maruti Espresso. So if I turn on the key, if a light is on, it will flicker. Why the heck it's flickering? Lead acid battery is almost like a capacitor, and it does have very good what you call surface charge level. That's how the batteries are designed. Is they are not designed as a deep cycle battery, but they are designed as a surface charge capacity. So they have bonkers surface charge, but the voltage stacks a lot. That is not only bad for, well, every electronic controller unit has to have reinforcement circuit to handle that. What if you can improve it by having a small supercapacitor? So you have 12 volt and you have supercapacitor. So whenever the starter motor just drains power, supercapacitor smooths it out. It's like, easy bro, easy, chill, and it smooths out the whole power rail. This alone increases the power fuel efficiency by 10%. I did not even know that's how big of an impact having voltage spikes has. Why? Because alternator has brushes. Those brushes send current into the rotor. So the moment voltage spike happens, that system starts to kick back in. And problem is like, it's almost giving a random load to your engine. Engine is like, what? So smoothing it out, nothing else. You are not creating new energy. You are just smoothing it out. Your engine is like, tada. This is from ELLOP, loop system. So you can even have supercapacitor to just smooth things out. Almost all EV have them. Some EV have them as energy storage, probably, and some combustion engine have this as like, buffering things out, which is a very wise way of utilizing it. You do not want your, lead acid battery to handle jerks. It's like, I got this. Capacitor is like, and what about lifespan? Trust me, if capacitor is cooled enough, that's the only penalty. It cannot be like, 80 or 100 or 200 degrees Celsius. So it has to be generally packed somewhere further back, as long as, or in some place where there is not enough high heat. As long as you can maintain that, it's like, bro, your car's bearing will wear out before I do. So hybrid energy sources. So hybrid battery storage, you have two different battery chemistry. Hybrid energy storage, you have two different topology, one faradic, one non-faradic. So what can we expect in the future? Well, this is a very fundamental limit on the chemistry itself. It cannot be bypassed. Like, it's like, oh, I'm gonna make a silicon solar cell that is like 50% efficient. Law of physics says, bitch please, you cannot do that. Like, there is a fundamental limit. We have figured it out. You can't exceed, I think 28 is the upper limit. Write it down below what was the exact limit, but you can't. So then how the heck military satellites have panels that are 51% or sometimes 55% efficient? Well, they have multi-junction solar. Instead of one junction, they have 3 junctions. Instead of just relying on silicon, they have arsenic. They have a palladium or I keep forgetting, gallium. Yeah. So they have 3 junctions that absorbs different wavelength, and that's how they get bonkers high power efficiency. So same applies into single cell chemistry. So you have sodium, it will behave different. You have lithium, it will behave different. Both of them on their own are weak. Combine them, now you're like, I got this. So the idea is you're gonna have sodium that is your oomph and cheap enough, and you're gonna have lithium that gives you range enough, where it's like cheap enough pack that low cost car can actually buy this, and it's have performance that actually make them feel not poor. You do not want your petrol car, which is not performance optimized, look like, and your electric car, which supposed to, everybody says, oh, instantaneous torque, you apply accelerator, battery is like, bruh. So that's the whole point. It's a very clever use. So mixing both of them solves the core problem of the current system. Like, what if somebody figures out a magical capacitor, which I know someone who's working on it, quantum capacitor. If it works out, and assuming it does not goes kaboom, that would solve this problem. But as of now, within non-faradic systems, within lithium ion, sodium ion, or nickel metal hydride, whatever have you, this problem would be there. So this is the only way of solving it without making it expensive. You can solve many of these problems, just make it a bigger. Yeah, people can't afford it. We'll keep consuming crude oil. So fundamentally, it has to be cheaper and high power plus fast control. Electronics does become more expensive. Let that be very clear. While the battery pack does go down in cost, the customer may not notice it. Although they will experience the lifespan, but the battery, basically it has a lot of DC to DC converter at full amp capacity. Meaning, if your system was designed at 500 amps of DC bus load capacity, the DC to DC converter should be able to handle almost all of it. So it not only like this sodium and lithium, that should not happen. Sodium should always be at, like, let's just say 50% discharge. Why? So it can handle the regeneration. So you will always take the power, dump it into lithium and slowly charging it up. And again, when you fully drain it, energy should not leave the lithium. Again, some amount, of course, but most of it should come from sodium. So that's how you're supposed to balance it. That requires active circuitry. So electronics does become expensive. And again, you can have way too many, which this company is trying to show, but I don't think you need more than 2. And practically speaking, I am more interested in lithium iron phosphate plus supercapacitor. That solves all the problem. Like, and again, at that point, I think you can even do truck hybrid systems, because again, truck has the worst problem. If I apply brake, it creates so much power, because again, you are talking about something that is 60 tons. Yeah, that creates bonkers amount of regen power. And again, power, not capacity. Capacity is minimal. It's just that you need that some place to just absorb it. It's like, so capacitor is like, I got the So this is a very futuristic development, and I like the idea. It's clever. It's not like, whoa, it's more like we have electronics. Electronics are becoming cheaper. So why not just have two different chemistry taking care of each other? Like, we literally put rebars into concrete, and we do not think about like, wait a minute, isn't concrete made out of water? So that's how it works. So this was my presentation on basically hybrid battery pack. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me excitement. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.